For number 7, we're dealing with interest, and we want to know how long we're going to have to leave this amount of money in the bank to reach this amount of money. It tells us our interest rate and that it's compounded annually. So you're going to use your interest formula here, and here's what all the different letters stand for. And so plug in the numbers we have for this problem. And since we're only compounding our interest one time a year annually, n is actually going to just be the number 1 here. If we were compounding monthly, it would be 12. If we were compounding weekly, it would be 52. But just one time a year, you get the number 1. So this is going to simplify quite a bit. When you divide by 1, it just stays 0.05. So adding that up, you get 1.05 inside. T times 1 just becomes T. And then my step to get from here to here, I divided both sides by 5100. So you get to this step, and we have the variable up in the exponent, so we're going to need to use logarithms to solve. We take the same logarithm of both sides, and then one of the rules of logarithms is if you have that exponent inside the logarithm, it can come out to the front and be multiplied. So now we have this number, and on the right side, t times this number. Divide both sides by the log of 1.05, and you'll get to this step. And now these are both just numbers, so do another division. That top number comes out to 0.34. The bottom number is right around 0.04. Reduce that down, and t equals 7 years. Another problem that would use the same formula is 26. Plug these values into the same formula we used for number 7 here, and then solve for the one variable that's missing. Number 9 is another interest problem, but this time we're compounding continuously. And the formula for compounded continuously interest is right here. A equals PERT, the principal times the number e raised to the exponent of r times t. And so again, plug in all your values where they go. And I'm going to divide both sides by 800. And you get to this step. Now if you take the logarithm, the same logarithm of both sides, we get to here. This logarithm is just a number. And over here, the logarithm of e raised to any value, these are inverse functions. So the ln and the e are going to cancel out, and you're just going to be left with that top part. Another way to see why that happens is, remember, you can bring this exponent down to the front and multiply it. And ln of e just equals 1. So you're going to have this exponent out in front multiplied by 1. And so the answer is just that exponent. Alright, and then from here we're solving for t, so divide both sides by 0.033, and you get the amount of time in years. 2 is a similar problem to what we just looked at in where we're using the number e again. To set 2 up, we need to note that we're looking for when we reach half of the original amount. So figure out what the original amount is. Plug in a 0 in for how many years have gone by. So if 0 years have gone by, we have the original amount. 0 times any number is 0, so e to the 0 power is 1. So the right side is just going to become 750. 750 times 1, 750. So the original amount is 750. Half of that is 375. So what you're solving for is when the amount is going to be equal to 375. So you're plugging in a 375 in here to the left side and then solving for the variable t. 8 also uses the number e. It's a little bit different than the ones I just looked at because you don't have to use logarithms. It's just asking us to plug in a 10 for the number of years. So you're going to plug in here a 10 for t and then just evaluate that right side and get your answer. Here's a couple more questions that would use that similar technique that I just showed in the video of taking the logarithm of both sides, which allows you to bring the variables down from the exponent and bring them down in front of the logarithm. A few more that deal with logarithms. Now, these next few are all going to deal with the properties of logarithms. And this is on page 419 from section 4.3. These properties of logarithms are just different ways you can rewrite the logarithm expression and have the same equal result. So for example, two values multiplied together, you can split up the logarithm to the log of the first value plus the log of the second value. So looking at problem 13, we have two values multiplied together. B to the 9th was multiplied by the 4th root of a. B to the 9th times the 4th root of a. So you can split that up and do a plus. And now you can, when you have the exponent in a logarithm, you can bring it down to the front. So you have 9 times ln b. And another way to write the 4th root is the 1/4 power, the 1/4 exponent. So we're bringing the 1/4 down in front. And now for this particular problem, they just wanted us to rewrite ln of a as u and ln of b as v. So I just make that substitution here to get the final solution. These two problems are going to similarly rely on the properties of logarithms, just to manipulate and rewrite the log in the way that they want. For 36, we have an equation here we're trying to solve, and again we're going to rely on these properties, page 419, section 4.3, in order to solve. So we have an addition here of logarithms with the same base, which means you could rewrite those with multiplication in just a single logarithm. And then I rewrote that the same thing here multiplied by itself is squared. So x minus 7 squared. Now in this next step, since this value is equal to 1, 9 to the 1 power should be the same as 9 to this power, because these values are equal. And now 9 to the logarithm 9 power, as our inverse here, we're going to have just the exponent left. So x minus 7 squared is all that's going to be left on the left side. And 9 to the first power is just 9. So from here, we just need to solve for x, take the square root of both sides, and you get to here. The square root of 9 is plus or minus 3, and then add 7. So for a plus 3 and 7, you get 10. A minus 3 and 7, you get 4. Now you need to check your answers. If you plug a 4 in here, we have a log of a negative number. Negative numbers are not in the domain of the log function. So this is not a solution. Only 10 is the solution for x. 37 here, again you're going to want to use the logarithm properties to rewrite this and solve for x. 46, raise both sides to the x power, or use x as the base and both sides, since these are equal, make them the exponent. And then x to the log x, that's going to cancel out and just leave you with 256 on the left. So you have 256 equals x to the 4th. Take the 4th root of 256, and again you get 2 answers. But it can't be negative 4, because if we go back to our original question, that would be log of negative 4. And you can't have a log with a negative value there.